Our last talk is from Jean-Louis Leroy.
Yes.
I hope I pronounced.
Au revoir, it's the same.
Okay. Open is good, so let's see what's going on with multi-methods.
Okay, good evening. I work for Bloomberg too, but I'm going to talk about a personal project of mine. What problem am I trying to solve? It's something called the expression problem. So consider that you have a polymorphic system that involves operations and types. And how do you extend it to new operations and new types? For the sake of reusability and composability, you would want it to be not only possible, but also easy, right? That is the expression problem. In C++, we have polymorphism in several places. At compile time, we have overloaded functions, which are a little boring, and then we have templates. And templates don't suffer from the expression problem. For example, take the Stepanov's STL. You can extend it by adding new algorithms, adding new iterators, and adding new containers. And as long as the mutual requirements are satisfied, nothing is going to stop you. It's extensible, it's open in 3 directions. So what about runtime? We also have several types of runtime polymorphism. We have function pointers, we have function objects, but the main mechanism for polymorphism here is the virtual function. If you want to add a new type to your system, you simply derive from a class and you override a virtual function or not. So you can add new types to existing operations. But what about adding new polymorphic operations to existing classes? Well, it's not that great. Let's take an example. An abstract syntax tree that represents a simple arithmetic expression. There's nothing complicated here. We have an abstract base class called node, which has a pure virtual function called value, which returns the value for the node. Number is simply a container for a literal, and plus has references to 2 nodes. It evaluates the right node, it evaluates the left nodes, it returns the sum, and we have the same thing for multiplication. And it works nicely. We can build a tree, and we can even erase the type of that tree from, let's say, times 2 to expression, and we call the value virtual function. It returns the value, which is, in this case, 14. Fine. Now, what if we want to add a new operation? For example, what if I want to render the expression tree in reverse Polish notation, you know, like HP calculators? So that should display something like 2, 3, 4 times plus equal 14. How do I do it? The most straightforward way is to simply add a new virtual function to RPN and implement it in the various concrete classes derived from Node. But this works, it's easy, but it has a problem. If you are also using my node hierarchy, you are getting the 2 RPN function, but maybe you're not interested in it. And maybe you're going to be more interested in adding, I don't know, a virtual function that writes to an host stream the rendering in JSON of the expression. And I'm not interested in that. And worse, I'm getting your virtual function, and you use the host stream, so I get a dependency on host stream, the IOStream library, which is quite a big thing. And Joe Armstrong, the creator of Erlang, had a very funny way of putting this. He said, the trouble with object-oriented programming is that you just wanted a banana, but you also got the gorilla holding the banana and then the entire jungle. And you end up, with God classes that gives you all the things that you don't want in the first place. Big problem. So we probably don't want to do this. What are the alternatives? We can implement a type switch, and we can try to dynamic cast the node to all the possible options, and throw an exception if no one matches. But it's a maintenance problem. Now, if we want to add new types, now that has become difficult. We could implement a visitor, and there are many ways of implementing visitors. Some of them do the traversal for you and so on. It's going to be a lot of code, but at least now you can add a 2 RPN operation without modifying the node hierarchy at the cost of deriving from the visitor and so on. It's a lot of work, but it's still a glorified type switch, meaning that we have exactly the same problem. Now we can easily add operations, but it has become difficult to add new subclasses of node. So not great either. We could use a function table or a function map. For example, have a map that associates the type ID, the dynamic type ID of the node, to a pointer to a function. And of course, we need to initialize that map before we can use it. But it's actually not bad, because if we add new types later, we can simply, another translation unit can add new entries to that table. So it's not bad, except that this doesn't understand inheritance. Okay, so let's have a quick poll. Only one vote. Which one do you prefer? Who votes for one? Virtual function. Oh, nobody. Oh, I'm glad to see that. Who likes the type switch? Who likes the visitor? Ah, a few. And who likes the function table? Okay. And what if I add a fifth option, which is they all stink? Who votes for they all stink? Yeah. I think that the old thing has it. So what's the alternative? In some language like C#, they have extension classes. In Java, they have libraries that implement aspect-oriented programming. All those are solutions to the expression problem. And one of them is actually quite an old solution. It's called open methods. So what is an open method? It's a function that is both virtual and free. It's a free virtual function. It's a virtual function that exists outside of any class, which means that you can add virtual functions without adding stuff to the class. Okay? YOMM2 implements open methods as a library. So this is the most important slide. I copied here the declaration of the pure virtual function to RPN from the virtual function solution. And just below, this is exactly the same thing, except that some things have moved around a bit. The function is not in the class anymore. A virtual function, being a member function, has an implicit parameter, which is the pointer to the current object, in this case, a const node pointer. That implicit formal parameter has become an explicit formal parameter. Virtual has moved. It has become a decorator around the now explicit current object parameter. In fact, it's not even a current object anymore, it's a parameter. And if we decorate the type with virtual, it means that we're going to consider the dynamic, the runtime type of that object when selecting which function to call. Let's look at an implementation of 2RPN. So this is, once again, a copy of the case with virtual functions. And same thing, here it's the same. The definitions have moved out of the class. The decorator is gone, but here we say const plus reference. So this says that we are overriding the virtual function, the method, for plus. And again, there's no this. The argument has become explicit. Okay, so now if you are familiar with common list for closure, the first one is called def generic in common list. In closure, it's called def multi. And for overriding in common list and closure, it's called def method. Okay, now strictly on this, because I don't have much time, I'll take questions at the end. Does anybody have any doubt about this? This is the most important slide. It's clear what it does? Any question about this? Okay. And here's now the complete AST solution using YOMM2 open methods. We have to include the library. We declare the method 2RPN. We provide definitions for each case. And we have to do two extra operations. We have to register the classes with YOMM2 so that it knows the inheritance lattice about nodes and plus and times. And once in the program, before calling any method, we have to call update, which is going to use all the information that has been registered via static constructors, and it calculates and creates the dispatch tables. And what about value, the value virtual function? Well, I'm going to surmise that it should also be moved out of the node hierarchy, because our AST is not very abstract. In fact, it's an AST, but for an interpreter. But what if instead I want to use the AST for compiling? I don't need the evaluation part. So I would say that value should be moved out of that class hierarchy, and the node hierarchy should just focus on doing the tree properly. But what's the cost of doing this? So assembler. YOMM2 implements methods very much in the same way as virtual functions, meaning that for each class, there is a corresponding table of pointers to functions, the V table. But there are two differences. In the case of virtual functions, when the compiler lays out the table, it already can figure out the position that each virtual function occupies in the V table. For open methods, it's more complicated because each translation unit can add virtual functions, methods, to existing classes. So it's not until the program is fully seen that you can figure out which offset each method is going to occupy in the V table. The other problem is that the compiler has an advantage. For normal virtual functions, how does it navigate from the object to the correct table? You all know it. It plants a VPTR inside the object, and it just has to follow it. How does YOMM2 do it? It uses a perfect hash of the address of the type info extracted from the object. So what is a perfect hash? It's a collision-free hash. We're going to have a talk later during the week, which I think will be very interesting. But also, the hash function I use is very simple. It simply take the pointer to the type info object. It's easy to find. It's you simply say address of type ID, and that pointer is stored at offset -1 of the V table, typically. So very quick to extract it. Convert it to an integer, multiply that by a certain number, and shift it to the right by a certain number of bits to keep only the upper bits. Very fast hash function. times shift. And then use the value as an index in a table of pointers to vtables. That compiles to 9 instructions. And please note, no loops, because the hash function is collision-free. So it compiles to 9 instructions, and as the grouping suggests, those instructions most of them can be executed as parallel pairs. So those 9 instructions actually amount to 5 sequential instructions. I can quickly go over it. This reads the VPTR, and at the same time reads the multiplication factor. This reads the address of the type ID, and in parallel we read the shift factor. And we shift the result of the multiplication, this is a multiplication too, by the set amount of bits. And then we use that as an index into the table of pointers to vtables. We read the entry of, so that gives us the vtable for that class. And then we have to read the offset that the method occupies in the vtable, and then we go to make the call. So okay, that's 9 instructions, but really 5 instructions, but that is still more than the 2 instructions that it usually takes to call a virtual function. If that is still too much, I have a solution later. But let's dwell on this. How do you measure the overhead of a function call? It's not something easy to do because, okay, I have spent hundreds of hours on benchmarks, and the results that it gave me was, I found it too good to believe, that method calls were within 15 to 30%, only 15 to 30% slower than virtual functions. But the body of, in my benchmark, the body of the functions do nothing. So very quickly, probably everything, all the data needed to dispatch either virtual functions or methods ends up in the cache. So does it mean anything? But if the body of the functions actually do some work, then 1, it's going to disturb the cache, and 2, the cost of the function call is likely to become very small compared to the call of executing the body. You just do a malloc inside the body, and then you won't even be able to observe the time it takes to make the call. So I believe that except in very specific situations, the difference is unobservable. If you're interested in a topic at CPPCon 2023, there's a very interesting talk about this. I linked it here. I'm often asked at this point, can you have more than one virtual argument? So the answer is yes. It is sometimes useful. For example, when you add 2 matrices, you want to pick, the right algorithm depending on whether it's just a plain matrix or if it's 2 diagonal matrices. And in normal C++, we do this by using, 2 virtual function calls. I call you, you call me back. And sometimes it's useful to have more than 2 virtual arguments. For example, in an adventure game, you have the player that tries to kill an adversary using some weapon. This is an example of triple dispatch. Well, good luck getting that right with 3 virtual functions. Now, please don't break my heart and don't walk out of this talk thinking and saying around, oh, yeah, YOMM2, it was about multi-methods, cool, but I never needed them in my life. The multi in open multi-method is just the cherry on the cake. The cake is open. The cake is the ability to add new polymorphic behavior to existing classes. And occasionally, you need multiple dispatch. And in that case, what is the rule for selecting the right function to call? I don't need to tell you, you already know it. It's exactly the same thing as overloaded function resolution. Meaning that, yeah, you can, shoot yourself in the foot and create ambiguities. The process of selecting the function will happen at runtime, unlike overloaded functions, and then some error handler will be called. So let's have another poll. Is this object-oriented programming? Who says that it is? Is it OOP? Yeah, well, does someone want to say why it's OOP? Yes, go ahead.
Because we're making polymorphic runtime decisions based on the type of the object that drives the action.
Okay. And who says that it is not OOP? Oh, only two. Well, personally, I'm sort of on the fence. So it is OOP in the sense that we have polymorphism, we use inheritance. Yeah, so it sounds like, you know, OOP. On the other hand, we're not focused on the object. The algorithm sort of retakes the front stage, just like in the STL. So it is not object obsessed, at least. And let's have another poll. Which one do you prefer? One of the all solutions or open methods? Let's go ahead. 1, 2. Okay, that's encouraging. Thank you. Okay, I knew I wouldn't have time for this because I want to talk about the past, the present, and the future, evolution of YOMM2. I've been working on open multi-method for quite a while, since 2013. There was a previous library, and YOMM2, I started working on it around 2017. And what were my goals? Well, to be honest, to have fun. But I also fantasized that I would help Bjarne Stroustrup get open multi-methods into the language, because that is something that he always wanted. Who has read Design and Evolution of C++? Yeah, excellent book. He says in it that right from the beginning, he wanted open multi-methods in C++, but he didn't know how to implement them. So he did templates instead. But around 2007, 2008, with two of his PhD students, Peter Pirkelbauer and Yuri Solotki, they made a big push at first implementing open multi-methods as an extension of the EDG compiler and trying to convince the committee that it was a good idea. And it didn't work. So I thought, since we couldn't get them brought into the language from the top, maybe we could try the other approach, which would be to go from the bottom up. And I thought, I'm going to write a library, and I'm going to submit it to Boost, and I'm going to talk about it. I gave a talk at CPPCon 2018, and for that purpose, I kept my library as a fairly faithful emulation of Stroustrup's ideas. There was a couple of divergences, but nothing important. And I kept it that way because I didn't want to obscure matters. And what's happened is that there was no interest in the Boost community. Or maybe I did a bad job at explaining, I don't know, but many people confuse it with overload resolution, so what's the point? The standard committee, well, okay, I didn't approach the standard committee, but it remained uninterested. And because my feeling is that these days, anything that is, compile time is super cool. Template metaprogramming and so on. And anything that involves inheritance is, okay, boomer. Absolutely uncool. So, I gave up on my hopes. I now believe that we will have a colony on Mars before we have open methods in C++. But in a way, it's liberating, because now I can go beyond what was in the Stroustrup papers and innovate again. So I'm going to go over a couple of those innovations. Probably the most important is virtual PTR. Virtual PTR is a fat pointer that caches the pointer to the V table along with the pointer to the object. I think that it is exactly the way runtime polymorphism is implemented in Rust and Golang, right? And the result is that if you call a method like value via a virtual PTR, it goes down to only 3 instructions. Moreover, when you declare a method, you can also declare it as not taking a virtual argument by reference, but by a virtual PTR by value, which means that, often when you call a virtual function or a method, the body is going to itself call more virtual functions. So it means that you can reuse that cached pointer several times. It is still costly to build a virtual PTR. Here you will recognize part of the code, the multiplication, the shift, that is the perfect hashing. So this is still a costly operation, but if you start organizing your program around virtual PTR, then there's no possible performance cost. And if you know for sure that the dynamic type of an object is the same as the static type, well, a typical situation would be you create it, right? You create a plus by newing it or creating it on the stack, then you are certain that it's a plus and not some subclass. In that case, you can use final virtual PTR. So final virtual PTR will trust you, and it will simply load the vtable pointer part of the fat pointer, well, directly from a static variable, right? Questions on this? Because now we have some time. Another, I think, important development was the publication of the core API. So what I've shown you so far, basically it uses macros. Declare method and define method are macros. The virtual underscore decorator is not a macro. It's a template. And I spent time cleaning up the internals and publishing and documenting many of them. And it makes it possible to use YOMM2 without using any macro. So why would you want to do that? I see 2 possibilities. You hate macros? Yeah. Okay, well, I mean, it's your choice. Or you want to use templates. And templates and macros, they don't like each other very much, right? And on top of it, the syntax for templates keeps evolving. So in that case, you can use the straight core API. And this is the value example again. You have to declare a type. You don't need to define it, just declare it, which will act as the ID of the method. And then the method, at its core, it's actually a type. This is more or less what declare method does. It says, oh, right, it uses the value ID to make it possible to have 2 different methods in the same namespace that have the same signature. That's why you need value ID, but you could use any type. And value, which is an alias or method of the signature, has a nested singleton called fn, which is a function object, and you can call the method like this. Okay. How do you add definitions to this method? Well, it has 2 nested templates, add function and add definition. Add function is a low-level thing. It takes a function and adds it to the list of the definitions for that function. There's also add definition. At definition, it's more or less it's the same thing, except that it takes not a function, but a class that is expected to have a static function called fn. And again, it adds that fn function to the list of definitions. Why it's better to use the definition? It has to do with something called next, which is the open method equivalent of calling the base version of a function. But I don't have time to get into those details. And what's interesting here is that you can use templates. Here, to implement plus and times, you know, they're both binary operations. I simply templatize my definition container by the node class which I use here in the signature of the function, and op, which is either std plus or std multiplies. And here I have added my two definitions for times and multiplies. To register a function, you need to create a static object of that type. But the name is really not important. So YOMM2 has a convenience macro that you can use unless you really hate macros. And that simply creates an obfuscated identifier based on counter, so you don't have to invent a name each time. But you can perfectly well use the core API without using that YOMM2 static macro. On the GitHub site, there is a sort of a lengthy and dense tutorial where I suggest patterns to blend open multi-methods with templates, and I also provide an experimental toolkit to help with this. So by using metaprogramming, you can get templated virtual functions, sort of. Well, except that they're methods. Can be useful. Another change since 2018 is that the library is now header only. You can still build it as a shared object. Has anybody used YOMM2 here? Oh, you have? Oh, I'd be interested to know what you used it for.
Well, I sometimes try code in Common Lisp.
Yes.
And I found that method and generic because I'm currently writing my bachelor thesis and it has to do with dynamic dispatch. So,
okay.
So I had to see what's there.
Okay, so one of the new developments is that you can use it as header only. You can still build YOMM2 as a shared library, but there's not much point because the runtime, that the update function, takes only something like 35K after stripping the debug symbols. And one of the motivations for that was to make YOMM2 available on Compiler Explorer. You can go to Compiler Explorer, it's there. You just have to select the library and select Boost because there's a dependency on Boost. And all the examples from this slide are actually available on Compiler Explorer. A while ago, I implemented support for friendship. Now, this is something interesting. In normal C++, when you want a virtual function, you have no choice but to also get access to the private parts of the class. I mean, why are those two tied? Because virtual functions have got to be members. It's purely accidental. Well, when you use open methods, sometimes it's useful for a method definition or all of the definitions pertaining to one method to be friends of a class. It is now feasible. We can have member methods, which is a bit anecdotal. And another important development, that's what I spent my last 8 months on, are policies and facets. So right from the beginning, method and use classes have a default template argument, which is called a policy. And so far, I used it for unit tests. and I cleaned up more parts of YOMM2 and channeled many operations through that policy class. And a policy is a collection of facets, and each facet is responsible for certain operations. For example, I use type ID in the library, but in some contexts that is unacceptable. Game developers, for example, they disable RTTI, and they use custom RTTI instead. Well, now this is handled by the RTTI facet of the policy, and you can plug in your own. There are facets for customizing error handling, tracing, even how you navigate from object to vtable. I have an example where a single pointer to the vtable is shared by an entire page of objects at the same time. And you can also use it to implement, to plant the VPTR inside the object, if the object wants to collaborate with us. So all this is already available in version 1.5.0, and I have ideas for future developments. I think I'll be able to, well, certainly match the speed of virtual functions and maybe go faster under certain conditions. I want to make it possible to pre-calculate the dispatch table. So that update function that we have to call at the beginning of the program, it's never called again unless you dynamically load a library that adds classes or methods definitions. But that's not the most common case. So in that case, why not pre-calculate the dispatch tables? And I'm going to add a facet that is going to be responsible for providing allocators for update, a temporary allocator for the data structures it needs to build the tables, and another one for the table itself. And the goal is to reach the possibility of a completely malloc-free operation. Here I'm thinking of contexts in which resources are scarce, like embedded programming. And I plan to implement dispatch on stud any, because why not? Almost all the mechanism is already there, the hashing of the fast hashing of the type ID. You can see that it's easy to add a dispatch on stud any. And at that point, I'll consider that YOMM2 is probably feature complete. And by then, I expect C++20 to be 6 years old. And I'll probably make the switch to C++20 and remove all the crazy Swine internals and replace it with concepts. Okay, so we still have a little time for questions. Okay, open questions.
I knew that you were going to make a question.
Well, yes, I'm interested in the subject, but regarding the allocator support, possibly malloc-free,
yes.
Is there currently, or perhaps I didn't understand well, will there be a support for providing custom allocators?
It's the future. The future is not the present.
Okay, that's. I'm interested in how you do that, so perhaps later I will talk to you or tomorrow.
It's not something very difficult. So I don't know if you want to get involved. You can send me a PR, or I can give you ideas about it.
Okay.
I do get PRs from time to time.
Okay, yeah. What I'm currently working on is not open multi-methods. It's something more like what other languages call existential types. But well, this information serves good to me.
Did you post something about it on Reddit a while ago?
Possibly, yeah.
Yeah, I think I saw it, yes.
Okay, thanks a lot.
Any other question?
Yeah, thank you for interesting talk. And the way the method register classes that you used, it reminds me a variant, because it also has a polymorphism based on visitor, which is in compile time via calculation dispatch tables. It's extendable because you have a default overload, so you can define like 3 or 5 classes and so on. So what is the differences? Because for me looks, especially compile time adoption, similar to stud variant.
Variants are closed. They're closed. You can use classes or register classes to incrementally add new classes. You see, the idea is that, let's suppose that I write a matrix library and I support, normal matrices, diagonal matrices, symmetric, square, and so on, but I don't have, let's say, sparse matrices, and you want them. So you're going to have to derive your sparse matrix from my matrix base, and you're going to have to provide implementations for plus, transpose, and so on, and you will be able to use classes or register classes and say register classes matrix, comma, sparse matrix, or the other way around, it doesn't matter. Because this is all incremental. Use classes at compile time, at compile time, it uses metaprogramming to deduce which class is a subclass of which. Unfortunately, we have no way of identifying a direct subclass. So it stores, partial information. And later, if you add a derived class, you create another record. And update, one of the things that it does is to take all that information and consolidate it, and it uses a coloring algorithm to extract the direct inheritance relationships from the transitive ones. So back to your question, variant is closed. Open methods are open. Other questions? Yes?
First, thank you for the talk. I want to ask you about some hypotheses. Have you thought about the possibility to do this in the running time, to add types in the running type? I mean, if you make some of the part that do the compiler with the dispatching the virtual function, it would be possible to use the load library and add in the running time a new library and put in the dispatching.
So
it's a little bit complicated, I know.
It depends to what extent you want to do that. If you mean creating whole new types at runtime, like you can do in Python, there's a library that implements that. It's called Dynamics. If you're talking about adding classes and methods and definitions at runtime, you can already do this using DL Open or the Windows equivalent. Dynamic loading is supported. But after dynamically loading or unloading a shared library, you have to call update again.
Yeah, yes. I mean, you call load library, you take the pointers and you put into the dispatcher, and you have like update in your table. I'm thinking in this idea if it will be possible.
Yeah, it's actually quite cool, because when you use DL Open or load library, you have to use things like get symbol and so on before you can start working with the code in the library. But if you use open methods, what's going to happen is that the runtime of C++ is going to execute the static constructors in the dynamic library, in the dynamically loaded library. It's going to register all that new stuff with the sort of catalog of methods and classes. You call update, it will figure it out. I actually have an example on GitHub that shows how to dynamically load libraries with new classes and new methods and new method definitions.
Thank you.
Any other question?
Maybe if I have time, I have a question for you. So, how comes I believe I can beat virtual functions? I already showed you that by using virtual PTR, I can get very close to the number of instructions virtual functions take. And it's by using that fat pointer like in Rust. How comes that C++ doesn't implement virtual functions like that? Why does it have to put the VPTR inside the object, which means that we have an extra indirection? So who has an idea? Why that wouldn't work in C++? It's not virtual inheritance, but it's close. Repeated inheritance. Repeated inheritance is a sort of killer because behind any virtual function call or method call, there is an implicit cast. And when you have two sub-objects of the same class within the same object, whether you cast from the left or from the right, it's a different offset. So that is why C++ in some cases needs to have multiple vtables for the same class, and YOMM2, that's maybe its only limitation, doesn't support repeated inheritance. Multiple, yes. Virtual, yes, but not repeated, because that that trick of hashing the type ID can get you only one VPTR. Okay.
Okay, thank you.
That's all. Well, good night.
Thank you very much.